Methanol is in 15, question 7. Methanol can be used as a fuel in a variety of different ways, and you've got a little picture of methanol in case we weren't sure. An increasingly common use for methanol is as an additive to petrol. Methanol has been tested as an additive in petrol at 118 grams per litre of fuel. Calculate the volume of carbon dioxide in litres that would be released by combustion of 118 grams of methanol. You've got a balanced equation given, and you've got the molar volume of carbon dioxide at 24 litres per mole. Okay, there are complicated ways to do this and easy. I'm all for trying to do the easy. Okay, here's methanol to carbon dioxide. Now, in the balanced equation, we can see that that's a 2 to 2. So that cancelled down really nicely to a 1 to 1. Now, what that means is that if I burn 1 mole of methanol, 32 grams of that, I will make 1 mole of carbon dioxide. But I'm not going to go to grams. I could say 44 grams and then do a change to litres afterwards. But what I can say is, well, 1 mole of carbon dioxide in litres is 24 litres. So 32 grams of methanol gives me 24 litres of carbon dioxide. So 118 grams of methanol, just do proportion. So 118 divided by 32 times by 24. I'd already worked that out. Where is it? Yes, 88.5 litres. And that's it. You can run the full calculation a little bit more if you wish, and it wouldn't actually matter if you put the 2 to 2 in, as long as you'd cancelled obviously when you were doing the next bit of the ratio. Student investigated the properties of methanol and ethanol. They carried out experiments to determine the enthalpy of combustion. So this is your standard stuff that you see for basic enthalpy of combustion. Okay. The student carried out the first experiment as shown, but was told to repeat the experiment as the thermometer had been placed in the wrong position. Suggest why the student's placing of the thermometer was incorrect. Okay, here is the thermometer. This is the problem. Okay, the thermometer bulb is obviously where you take the temperature, and that is actually not taking the temperature of the water, it's taking the temperature of the beaker. Okay, beaker temp, not water. So we need to not do that. Okay. The student always used 100 centimetres cubed of water. Grand. State another variable that the student should have kept constant. So really, what I'm expecting is the distance from the burner. So obviously, if you had the beaker and you had the burner, set up underneath it, burning away quite happily, and then you'd gone and got another setup, and your clamp stand had actually ended up with the beaker now slightly higher, this is going to cause, this gap here is going to create more potential for loss to surroundings. So that's not acceptable. And honestly, I was just like, well, surely that's the most common one. But I went and looked at the mark scheme for this one, and what we had was also the wick in the burner. So the size of this point, the wick here, because obviously that would draw greater volumes up if it was longer. And they did say the type of beaker would be acceptable, but only if you were more precise about that. So if you said that the metal beaker should be made of copper in both, or should always be aluminium, or as long as you did, because at the moment it just says metal. Okay. And then there also was the idea that you might want to put the draft proofing around the outside to try and prevent issues of movement of heat. But actually that's an answer further on. So distance from burner is what I would expect. The student burned 1.07 grams of methanol and recorded a temperature rise of 23 degrees C. Calculate the enthalpy of combustion in kilojoules per mole for methanol using the student's results. Okay, right, so this is your kind of standard one to do. There's nothing actually really complicated about it, but it's worth 3 marks. You're obviously doing quite a bit of calculation. So we're going to start off with delta HCm delta T. 4.18 is our C from back of data book, and our mass, being very careful, remember this is mass of water, it is not the mass of the methanol. So it was 100 centimetres cubed, so put it into litres, so 0.1. And then our temperature rise, it said, was 23 degrees. So that's our kind of baseline that we need to work with, and that is 9.614 kilojoules. So that was how much we got from 1.07 grams. 1.07 grams gave me 9.614. So then I need a mole. I need 32 grams. So 32 divided by 1.07 times by 9.614 gives me 287.5 kilojoules per mole. There's your answer. Okay, so for 3 marks, it could look quite small if you've done it by proportion working your way through. Okay. Right, the student determined the density of the alcohols by measuring the mass of a volume of each alcohol. Results are shown below. We've got volume in centimetres cubed, mass of alcohol in grams, density of alcohol is grams per centimetre cubed. Now this tells you, your calculation, because what they're saying is it's that divided by that. So I am doing that divided by that, and that gives me 0.799 grams. That's it. Methanol is used as a source of hydrogen for fuel cells. Industrial process involves the reaction of methanol with steam. We've got a little picture. Equation. State why it's important for chemists to predict whether reactions in an industrial process are exothermic or endothermic. Right, so really, this frankly I think is all about safety. Okay, you need to know if it's exothermic because you may have then a requirement to remove heat. Okay, you then also might have a requirement so you might have an energy requirement to give heat. And from an industrial point of view, you could also say that this is all about yield. So you know that especially if it goes to an equilibrium, that you're going to have to run that as well. Sorry, just ignore little pop-ups. Okay, using bond enthalpies from the data booklet, calculate the enthalpy change in kilojoules per mole for the reaction of methanol with steam. Now, again, I think they've been relatively nice because they've given you all of the data in terms of which bonds, they've drawn them out for you. And generally that's how I would probably draw them out, or I might have drawn that. The 3 there just so I could see them clearly. Right, so what you've got to remember is in a normal equation, okay, you have to go up and then you go down. That's the reaction pathway. So I'm going to break, and that's going to be plus, and then I'm going to make, and that's your minus. You've got to take apart your entire Lego house before you build your Lego boat. Okay, right, so we'll do our break first. So our break is going to be 3 carbons to hydrogen, and then we're going to break 1 carbon to oxygen, and we're going to break 2 oxygen to hydrogen. So that's 3 times 412, 1, 2, 3, 6. That's just 1 times, so that's just 360. And we've got 3 times our 463 here, giving me 1,389. Add all that up means that my initial breaking is going to be a plus 2985. Okay, then I'm going to make everything. So I'm going to make 3 H to H. So that's 3 times 436. And that's 1308. In an exam, I would really, I would recommend writing it out fully so that when you're doing your check at the end, you can check that you actually have every single bit of it right, that you've put down the right enthalpies, like at these points here, and that you've actually done the calculation correct to get your final one. Minus 2794 is our make, and then all we do is add them up. So plus 2985 minus 2794 gives it my total as plus 191 kilojoules per mole. Done. And done for the question.